God, the cloud. Cool. So let's talk probabilistic programming. First an overview, then a bit of math, and then a bit of code. And this is largely based on, at least the code is largely based on the probabilistic AI school that I attended, which was super cool. I would highly recommend the lectures. I've already shared the links with you. And there is a nice GitHub repository with a lot of code to follow up. I'm also down to discuss that over the next few weeks. If people want to present what they learned from that or just the code that they have. I should also turn off my video to save some battery. Okay, so you already, so this was originally prepared for my a certain bio reading group. So there were some bio folks who wanted to learn more about this. So I'm just giving them an introduction to myself. I can skip over that. We already had that session with the people here. Let's get to a rather biased history of programming languages. And this is motivating more than like which languages were developed or the order in which they were developed. Just what did the language bring to the table in a very opinionated way. So C was an imperative procedural language starting at the extreme left, right? So when C came about, they said, look, there is a slightly higher level language than machine code that does multiple machine level instructions in one line of code, which is why procedural. C++ came about after, so C was Dennis Ritchie, then Bjorn Strustrup made C with classes, which was the precursor to modern day C++. So classes were the real advancement there, among a lot of other things. Python came about saying, look, we are opinionated. There is one and preferably only one way to do things. We want people to adhere to certain paradigms. And it came about with dynamic typing. I should have mentioned that before. Okay, that's the next slide. Then we have PyTorch, we did automatic differentiation and deep learning. And finally, modern times, modern since 2017, Pyro has been unifying the best of this modern deep learning and Bayesian modeling. So really, probabilistic programming is all about scaling Bayesian inference to larger and larger data sets and applications. Right. So again, the same things in a different way, from low level to higher level to higher level to higher level to highest level. Well, in a sense, we have so far. So from procedural instructions to classes to dynamically typed languages to automate dynamic typing just means you have a lot more runtime type checking and errors. Whereas in C and C++, you have more of compile time stuff, right? PyTorch, on the other hand, came about with this automatic differentiation. So it built on AutoGrad, and it had random variables and distributions. Pyro used these random variables and distributions and said, now we will introduce conditioning and inference. So yeah, that's what I want to say. And of course, a more complete picture or a less biased history would involve a lot more languages, but I'm not getting into those because it's not relevant to get into those. I'm just mentioning that so that you know that there are a lot more things out there than I'm explaining in the slides. And if you start from the left, like what you do in computer science or regular programming, as you might say, you have a function. The function takes some parameters. The functions are used to compose a program, and the program is run to create some output, right? In probabilistic programming, you have the same things, but the order of execution is slightly different. So you start with some observations that you might have, or you infer. So you start with some observations. You go back and think about the program that could have produced these observations, and then you want to get as output the parameters that could have produced these observations. So that is really the key idea. Like this entire backward step is called inference, which is equivalent to what statistical inference is, where you observe some y, you go back and you know that this y was produced from some model, and there was a prior place on some parameters. And then you want to infer the posterior of these parameters x given some observations y. And you might think of x as theta in other cases, or w as weights, but it's essentially the same thing with a different notation. Some unobserved quantity inferred from some observed quantity. Cool. Any questions so far? Okay. So one thing you have to think about is these arrows still move forward, right? In probabilistic programming, we still go from parameters to program to observations. So we're still writing out some, like, physically, we're writing out some program with some parameters. We are just running it in a sense where it is conditioned on these observations to infer the parameters. So we still have some sort of model for the world, that we assume is this true process. Then we write a certain guide function that uh, 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 we claim is our simplified version of the true world. And then we update this guide to get as close to the model as possible. So the model we have of the world might still be wrong, but the goal is, like, at least the guide gets closer in this space that the guide has at hand. So the domain of the guide, you find a good candidate in this family of distributions that is specified by the guide. That is the correct mathematical term. So you get the guide closer to the model, but this model is still our version of the world. It's not necessarily the perfect world, and that's important to note. The model is just there for, like, technical reasons, where you want to write down, in an ideal world, how would my data be generated, and then the guide is like, okay, but really, what can I do? And I'm highlighting this difference here because, like, when I show you the code, a lot of people get confused by the difference between model and guide. So in terms of, I'll get to variational inference in a bit, and I'll discuss more there. So in computer science, like, you have just one program, and you run this program, you get some output. But now our goal is, we don't really know the program, so we make some assumption of how the program might be, and then you want to infer the parameters to this program. So that's sort of the difference between these two things. Yeah. Again, I'm not being very precise here, because that there is, the program encodes your assumptions about the world, and then based on those assumptions you can infer the parameters. But yeah. So in terms of, like, where it lies, probabilistic programming lies at the intersection of machine learning algorithms. So all of this deep learning and Bayesian inference is combined. So you have stats on one side, you have machine learning on the other side. You combine these two to get probabilistic programming. But there's also hardware level optimizations. So if you remember, I said Pyro builds on top of PyTorch, but PyTorch does a lot of hardware-based stuff. Like, a lot of it is relevant to GPUs, TPUs, and all of that. So it's super important. What's the difference between probabilistic programming and machine learning? There's a question, right? So great question. There is no difference. Probabilistic programming advances machine learning in a direction that says, hey, look, like, with machine learning, you can do prediction, but now with probabilistic programming, you just learned about posteriors and priors and all of that. So you can do those kinds of things with uncertainties over your predictions. And that's why I said it's an advancement, because it can still do the same things as machine learning, but then it has more, in terms of Bayesian inference. And like I said, there's a whole purple circle, which is programming languages, compilers, semantics, transformations, amortizing inference, and whatnot. So general idea being, inference has a lot of technical things going on. So in old days, what happened? I should have a slide here, but yeah, I'll get to that. Cool. So the challenges that probabilistic programming addresses is scaling Bayesian inference, which has classically been pretty hard. So it's been an active area of research with encouraging results for specific problems. And what do I mean by that? Okay, so I'm going to pause for a second as Manav connects to audio, just so that he's on board for this part. And he probably thinks I'm frozen. This is great. Okay, never mind. I'll continue. So what I'm saying is, a decade ago, people used to say, here is a custom forward model. Here is a custom algorithm to perform inference over this forward model. Now, what do I mean? What I mean is, if in this in this world there is a certain model for weather, then I will have to write a specific algorithm for this model of the weather to infer based on what the weather conditions were, what could have been the parameters, like what could have caused this weather. And I have to do that. I have to write a new algorithm for every single model that I define. And as you can imagine, that might be quite tedious because typically for if you have a data set today, the first thing you do is throw linear regression at it. The second thing you do is throw neural network at it. Third thing you do is probably throw a more complex neural network, try to play around with it, right? Imagine having to write a custom algorithm to do the learning each time you wrote this forward model. That's what people used to do before, and you can imagine why that is so tedious. Today you just do uh, loss.grad or whatever, um, um, and you get your gradients and backpropagate them and learn. And imagine having to write the custom backpropagation code for each model, not for each problem. The same problem, different models, custom code. It's insane. It's like saying for every file you read, you have to write a custom file parser, and that's just crazy. So that's why, like, when someone came up with general purpose inference algorithms, when they said, look, whatever sort of model you write, whatever sort of file you have, I have a parser for it. That was like crazy. People just like really, really, really appreciated those black box algorithms. That's what they're called. They're called black box algorithms or black box variational inference in this case that we're discussing, because it doesn't rely on a choice of forward model. It works for all different kinds of models. And so that's what this next slide tells you, that it is essentially modern probabilistic programming languages are commodifying inference. So given any forward model, we can use the same inference algorithm. These are just graphical models representing different forward models. So yeah. So the emphasis is on deep universal probabilistic programming. Universal refers to the fact that any computable probability distribution can be expressed in this language. And you might ask, what is an uncomputable probability distribution? Well, there are implicit ways and explicit ways to define these things. I think that is what it refers to. I don't know the correct answer there. But yeah, that's the idea. Anyway, so probabilistic programming does for Bayesian inference what automatic differentiation did for deep learning. That is my opinion. Like I explained, the analogy. And finally, what I want to talk about is this whole idea of simulation-based inference. So in simulation-based inference, what you are doing is you are saying, here is a forward model or a forward generative model for a process. So suppose it's an admission into MS universities abroad. Here is how the data is generated. First, you take in the the grades, filter by grades, then do a semantic analysis of SOPs, match to professors, filter by professor funding, and then admit to PhD program. If that is a forward generative process, then I now, after proposing that, I want to collect real world observations of this process. So I want to collect your data, your SOPs, your grades, your whatever professors you're interested in, and your admissions. So my X and my Y, that's what I collect. And well, I shouldn't say X and Y. I should say Y, it's like observations. And now I want to use these observations to condition this process. So I have to go back and infer how likely it is. So if I originally thought that grades were very important, after running this update procedure, do I think the grades are still super important? That is what this posterior distribution tells us. And finally, I want to use this fitted model. In many cases, I want to use this model to make new predictions, which is called the posterior predictive distribution. So on a new test data point, can I predict if they will be admitted to a master's university or not based on whatever data they have? So yeah, that's the goal here. Okay. So having said that, let's jump into some math. This is a really bad time to join the call, so don't be scared if you see us doing. a lot of math because we've gone through the easy stuff, but the code is left. So I would, if you're really interested, I would advise you stick around until the code. Okay, but I will walk through the math. Question from Deep: would the posteriors keep changing significantly if new parameters are calculated with new data? Yes. Significant is dependent on how far off your prior is, right? So if you say my prior is something very wrong, then yes, your data will probably move it very far from its original place. But if your prior is already pretty good, then your posterior would not move significantly, if that answers your question. Okay. Okay. Let's share screen. Yes. So most of you have heard of Bayes theorem. I'm going to just formalize some notions for it. Y is our target, X are our predictors, D is our data set, where we assume we have IID samples, independent and identically distributed. Theta are our parameters, which is weights and biases. And they are independent of each other. So this is just indicating the joint probability is a product of marginal probabilities. And so Bayes rule states that, P of theta given D is equal to P of D given theta times P of theta by P of D. These things individually are called the posterior, the data likelihood, the prior, and the marginal likelihood of the data. Or this is equal to a nasty integral. I'll tell you. I'll tell you about this later. And so you know all of these things, right? Now what I'm trying to go for is to say that in Pyro, what happens is you have a certain data set and you have a certain model, right? These two things are with you, and you want to use these to predict this thing. And there is a certain way you approximate this nasty integral in the denominator. Why is this a nasty integral? What you are saying is, I will marginalize my data over every setting for theta. So over every possible model. Um, um, and that is next to impossible for a very wide model space. Yeah, I don't know if I want to say more about that. So essentially in Pyro, given the model and data likelihood, you want to predict the posteriors for your parameters. And Pyro, so this estimation procedure is called statistical inference. So this theta given D is an estimation. It's not a calculation. Remember that, because in most real world problems, this is not a tractable integral. In some specific cases, this integral might be tractable, but otherwise you cannot calculate it. It's like saying, try out every different model in machine learning. That's not possible. That's very unlikely for you to do. So you can still pick certain candidates and try those out, but it's not possible to check every single candidate. That's all I'm saying. Right. So that's why this is an estimation and not a calculation. Now, there are many different algorithms for statistical inference that are model specific that we discussed. Like, for instance, if you have, like, I showed you the different kinds of forward models, and there is an algorithm for each of those. Equivalently, there can be one for logistic regression models. But the real cool stuff came in with general purpose algorithms, and I'll talk about those in the notebook. But essentially, what general purpose algorithms are saying is no matter what forward generative model you give me, I can calculate I can infer the posterior over the parameters given some observed data. So and I want to caveat by saying this is true for any computable probability distribution. That is how you say Turing complete, right? This any also has to do with Turing complete languages. So yeah, that's all I wanted to say, that there are still some restrictions around this, but in general, this is what we are trying to do. So I'm not going to get into the posterior predictive, but I can jump to variational inference. So remember that we care about P of theta given D, right? And theta we said was W and B. This is the posterior, or in just English, what is our updated belief? Cool. There is a certain prior belief that pineapples and spinach do not go well on pizza. And then we make some pizzas with pineapple and spinach, or we see someone eat these pizzas, and then we update our belief saying, hey, well, he liked it, so maybe there is some truth and we should try pineapple on pizza. So that's a process of updating belief, and your model is doing the exact same. It's saying, okay, maybe my theta lies between 0 and 5, and then after seeing some data, it's saying, okay, maybe it lies between 2 and 3, so it narrows down the space. Or maybe it says it does not lie between 0 and 5, it lies between 6 and 8. So it also depends on what support you give the theta. Like if you restrain theta to be between 0 and 5, then it can never find the values between 6 and 8. It'll just go towards 5 and stop there, right? So yeah, so again, what we're doing is we are approximating it being the model with a guide distribution Q. So we want to find this true posterior, but we know that we can't calculate it. We have to estimate it. So we are saying, let's propose a certain distribution Q, a certain family Q, and approximate this P with this family Q. This Q is also called a variational distribution. And as you might see, now we're getting to this part about variational inference. And Q is parametrized by this set of parameters phi. So we claim the posterior is approximately equal to this random distribution that we have proposed, or to be more precise, this random class of distributions that we have proposed. Because this phi is an individual candidate. So Q is a class of distributions, Q phi might be one distribution within this class. So it's like saying the class is normal distributions, and the normal of mu comma sigma is this candidate within this class of normal distributions. That's the difference, right? So this is Q psi, this is Q, the family. Okay, hopefully this is clear. And so we're saying, how do we find this Q psi, right? You start somewhere in the class of normal distributions and you optimize your mu and sigma until you get to a point where you're confident that this Q, if psi is mu and sigma, then Q sub mu and sigma is a good candidate to approximate this P. Right, that's the procedure here. And how do we do this? I feel like I should skip the math here, because there are, how comfortable are people out here with this much math so far? On a scale of 1 to 10, you can DM me or just post 1 to 10 on the chat. The question again is, how comfortable are you with the math so far? Jay being a baller.
Swapneel, I also had a doubt. So, can you give an example of like what sort of like how this general purpose algorithm like have is able to compute like the backward or the inference part like for different algorithms? So, like, is there something like what makes it sort of some way like that it computes? Like we just write the forward and it computes like the inference part directly on its own. Right? Are there not any constraints based on the inference like for different specific scenarios or
So that's a great question in general. And earlier, maybe I didn't emphasize that in the slides, but the point was to get okay, I don't see. Yeah, I got just 3 people polling, but anyway, the point was there is this abstraction layer added in the middle. Um, okay, let me just go back to the slides. Yeah. So this abstraction layer allows you to express these models in a language where you can then do general purpose inference. Before this, there was no abstraction layer. So there was no unified way of representing these models.
Okay.
So now
But
what this abstraction layer does is just express these models as sets of random variables.
okay.
Right? And now sets of random variables, you can then define a general algorithm to perform inference on.
Okay. But is this sort of like general proof algorithm like true for every problem, or like are there sort of some constraints based on this particular algorithm as well? Like sort of like for what specific scenarios might it work or might not work, sort of. Or like it works on any algorithm.
You are right that there is some scaling, there are still some scaling issues with modern inference libraries. They can scale, but like there are still challenges that they deal with, and there are still like these, sorry, excuse me. There are still like these discrete random variables that some languages face a challenge performing inference over, because they have to consider each value of this random variable as opposed to this optimization that they can perform. And so there's this enumeration procedure involved, and that just blows up the space. So yes, there are challenges. Yes, it is still an active area of research, and that's also where like all of these hardware level optimizations come in, that oh, now we can use gradient based approaches to learn this stuff.
Okay, got it.
Cool.
I
Random
I have.
variables.
Oh, sorry.
No, go ahead.
I just had one follow-up question to what I had asked earlier. So here, when we calculate the parameters based on the data, so we are assuming that the data is a representative of a complete population, right? Because if not, then again, if we introduce some new data, then the posteriors would change significantly from what we had calculated earlier.
Exactly, and also that is an active area of research called domain adaptation, right? Invariance, domain adaptation, robustness. There's a particular term for this. A distributional shift. All of these things refer to this idea that your training data is not from the same domain as your test data, and somewhat also tie in with this idea of if you don't have a representative sample, what do you do? And generally, if you don't have a representative sample, you're not going to be good. So that's more like an unlucky thing. With training and testing, that is a very common problem. Like your training data will not be the same as your test data, like is often not the same, not in the same domain as your test data, just because time-based shifting is a real thing. Are random variables a basic unit for, I'm assuming I answered your question.
No, so I wanted to know like the main difference between tensors and random variable is that like for the it's easy for like to simulate it randomly from a given function. So like because random variable would be like n-dimensional arrays, but then in order to fill them like randomly, like maybe some from distribution that we uh, come up with or that we provide to the model. So like the main difference between the random variables and the tensors in these languages is just like the randomness basically. Is that it?
I believe so. Yeah.
Okay, cool.
It's also to speak to somewhat like to my understanding of how this inference works. I think what they do is like simulate a large number of values and then cut out the values that don't fit into this condition distribution. So I think that's how conditioning is implemented, but I'm not exactly sure like how they've weird. I'm sorry. I'm not sure how they have set it up internally, and it's a good question. I should definitely look that up. But that was very like if you're super interested in that, you should look up that implementation, because that will give you this practical connection between, is this just random variables and conditioning, or like is the practical implementation something like simulating a large population and then cutting out parts of that population that don't fit into this condition distribution that they have, or conditioning by cutting out. I don't know.
Yep, makes sense. Thank you.
Sure. So let us go back to a bit of math, and I apologize, I'm 6 minutes over time. I should have jumped into the code by now, but I just wanted to give you a sense of what people do in variational inference. Am I sharing? No. Cool. So essentially what you're saying is Q is a family. Q is a family of distributions. And this is a random space that I've just generated, which has no geometric meaning, but like in a hand wavy sense, there is some limitation on the what the normal distribution represents. And Q phi is a candidate in this family of normal distributions, right? And the goal of variational inference is to take Q from Q phi, which is a random candidate, to this very good candidate that is very close to this P. So Q phi does not contain P. So Q phi cannot ever get to the point where it says this is equal to P, but it can go along this path. Sorry, should start from here. It can go along this path to get closer and closer within the space of Q to a point where this KL divergence, or this distance between P and Q, is extremely small. So that's what this line is representing. And that's why in the last lecture we discussed divergences and distances, because in the space of distributions, it gets more complicated than in the case of just 2 points. So we are minimizing this divergence and finding the distribution within this space of models, or within this class of distributions, or within this variational family that that minimizes this distance between the two distributions. And there is some math for why we use this and how it goes through. I don't feel like that is super important. So I will skip this right now, but I will share this with you so you can reference this. I will erase these notes that I made about this before, so you're not distracted. Yeah, okay. So I'll stop with the math here in the interest of time. Now I'll go back to sharing my, not this. Where is my code? Oh, there it is. Cool. So this is a notebook. I'll share it right after the lecture, just implementing some basic stuff in Pyro. Showing you what is a model, what is a guide, why do we want the guide to be close to the model, what we are doing with variational inference. Variational inference is this algorithm that gets your guide close to the true posterior. You don't know the true posterior, which is why you need a model for the true posterior, right? The guide is where you start. The model is hopefully where you want to end up. The guide may never be able to approximate, they'll never be able to exactly match the model. And the model may never be mapping to the real world. But the best you can do is get everything as close as possible. Is this, I'll pause here. Is this clear to everyone, like what I'm saying here? So there is a world out there. There is our model of the world, and there is the assumptions we are willing to make to get to that model. Cool. So this is showing you that okay. So we start with Pyro's distributions. So we have something like, say, the normal distribution in Pyro, and then this has a default mean of 0 and a scale that is set to, it's set in this case, but it's also default 0, 1. You can sample from this normal distribution, and the sample would look like something like this because it's a random sample, it's a tensor, right? If you resample, you'll get some different value. If you resample, you'll get some different value. So it's a stochastic function, right? And now you can sample multiple values. So each time you resample these values, you'll get resample, you will get different values. You can do some basic stuff like query the sample shape. You can do stuff like calculating the log probability or log likelihood of this sample. So we discussed this just in the lecture before, like under this model, under this normal distribution, what is the log likelihood of this data set? So, and we said that because this is IID data, we can just take the individual log likelihoods and we can sum them up. So there is a certain number that is output as the log likelihood. This is not a random variable, right? So given a sample, the log likelihood is fixed. But the minute I change my sample, now this sample will have a new log likelihood. Why am I? Oh, sorry, this is still the log probability. This is a new sample. No. This is a new sample. New sample, new log probabilities, new value for log likelihood. Everyone still with me? Okay. If not, then pause. We can always pause and re-look at something. Cool. Okay, so far so good. Sampled from the normal, got the log probabilities. This is great. Now let's say that I see some temperature in the world, right? And the way I see this temperature is it's measured by a sensor. So I want to, yeah. So this is the true temperature in the world. I don't know how this occurs. I have a sensor that models this that measures this temperature. My sensor is noisy, doesn't measure the perfect temperature. So the way I define this model of how I think the true world works is by saying there is some temperature that is drawn from a normal distribution. This is a random variable, right? It is named temp. Then there is a sensor that measures this temperature. So it is drawn from the temperature as the mean. So it is drawn, a value is drawn from around the true temperature, but it has some variance. So it's not perfect. It's still a random sample. And so this model returns the value of the temperature in the world and the measurement by the sensor. So if I run this each time, it will randomly draw a true temperature. It will randomly sample from somewhere around the true temperature with some error. Are we still good? This is a model of the world. This might not be how the true world works, but this seems to be our understanding of how the true world works.
I just want to be clear on one thing. So the sensor has temperature in the normal distribution because temperature is the expected value, right?
Correct. This is an excellent point. So on average or in expectation, you would expect like the sensor converges to the true value of the temperature. But every measurement might not be exact. But if you take like 300 measurements, then on average, you would be very close or exactly close in this case. So each time you run this, you get different random samples out, like we discussed before. This is a stochastic function. So the model is a stochastic function. Each time you run it, you're probably going to get different values out. And another way of looking at this is now you're defining a joint distribution of two random variables, and you're saying they factorize as probability of temperature, which is independent, given probability of sensor conditioned on temperature, because this is now a parent of sensor. So temperature times sensor given temperature. And that's how the joint factorizes, which is based on the dependencies. But because we're in a probabilistic programming language, we can also have more complex dependencies, right? So I'm not jumping into inference yet, but first let's jump into conditioning on this on some observation. So suppose we have some observation of sensor value which says 18 degrees, and the question now is, if the sensor says 18 degrees, what is the true temperature, right? And we know that this is a certain model for the world. We write a guide for this model. The guide encapsulates what we are willing to say about Q. We know that we can never get to P. But that being said, we have some Q that we want to be able to approximate P. So this is what we're trying to do. That's about it. What do I want to say about this? Cool. So now the way we define this model is we are saying, given a certain observation, you want to condition the sensor value on this observed value for the sensor temperature, right? And I don't know what else I want to say about this. Yeah, I guess one more thing I should say is that, like, now you want to get the output as these values A and B, right, for the temperature mean and temperature scale. And so while this encodes the assumptions you have made about the world, you really want to get output as this inference of these parameters that are of interest to you. So I guess I probably haven't run a cell above. Yes. So this is a stochastic variation inference cell, but right now it's not super important to go into that. So far we have a model that encapsulates how the world might work. We have a guide that encapsulates the assumptions we are willing to make and the parameters we want to find. The goal is to get sorry.
So, like, what is the role of constraint here? Like, constraints are positive. So, like, what does it indicate? Like, the correlation is in a way positive, or like,
This is a great point. So, because we parameterize this normal distribution with a variance of D, we need the variance to be positive.
Okay.
So already,
but like in like, are there cases or like it's a general assumption that we assume that the model is sort of positively constrained like based on this particular parameterization?
This is just a constraint on generally, like, parameterizing normal distributions, that any sort of variance has to be positive. If it is not, then we have a problem. Like, you cannot claim this is a normal distribution with a negative variance. There is no such thing as a negative variance, right?
Yeah.
So then this distribution would not be defined. So that is why we place this constraint.
Okay. But then this is like true for all the distributions, right? Or exactly like those who are in sort of similar to normal distribution that are defined. Sorry, I
Yes,
didn't.
this is true for any normal distribution. If you have a parameter, you will have to add a constraint start positive. Otherwise, B might be negative, and then you're like, wait, how do I sample from a negative distribution with a mean and a negative variance?
But like if you see, we define like there are sort of this particular parameters with mean and like the square of with the variance, like square of standard deviation, right? Sigma square. So then if we like have the scale parameter, let's say negative, then also it should work, right? I don't know exactly if that might be true, but yeah, like this is
This is a good point. Let's see.
because we define like covariance matrix at a sigma square.
No, you're right. I forgot that scale was, not variance. Okay, apparently it still works. So this is the learned values of the location and the scale, right? So it's saying temperature is centered at around 17, and it has a variance of about, it has a standard deviation of about 0.93. Interesting. Well, I don't know what to say. I've never heard of standard deviation being negative. Like standard deviation is distance from the mean. What do
Yeah,
you mean by that being negative, right?
that is true.
So I guess like the constraint is just so that to avoid errors of that nature. What did I do?
I think it was about sellable. Yeah,
Yes.
like this should
Yeah,
be
that's a.
on safer side. Okay, yeah, it's a assumption.
I think so. But yeah, that's fair. Cool. So what we did was we ran an inference procedure and we said we want to solve this Bayesian inference problem, right? We want to find the probability of temperature given sensor is equal to 18. We have one observation that the sensor value was 18. And we know that the probability that we formulate this as the likelihood of the data times the prior over the normalization constant, right? And so this normalization, this denominator term is super hard to calculate. So, oops, sorry, should not. This denominator term is super hard to calculate. So we estimate it. This estimation requires stochastic variational inference. How do we estimate it? We takes again, I'm not going to go into the variational inference algorithm. We can do that separately. Deep asks, is there a specific reason why temperature has mean 15 in model? No, not really. It's just an assumption they have made about the world. Yeah, I want to get into stochastic inference, variational inference, but also like we skipped over the math for it, so it'll be hard to just jump into it. So instead of doing that, I will jump a little further and like talk about this case where I'm learning from a bunch of observations now. So I want to talk about like now we're doing maximum likelihood estimation. You can think about it in a way as maximum likelihood estimation. Now we're not yet jumping into variational inference. All we are doing is given a certain model, we want to maximize the likelihood of this data under this model, obtain certain parameter estimates, and provide them here. Here is if this is the model, if these are the parameter values that maximize the likelihood of your data. So this formulates the same problem, argmax mu that maximizes the log likelihood of this data set S1 to Sn given the mean is the same as argmax. You integrate out this ti variable. So the Si given Ti is independent of the mean. So Si given Ti mu reduces to Si given Ti and then Ti given mu. That's it. You want to integrate over Ti so that you get Si given mu. And then you want to find the argument mu that maximizes the likelihood of this set of observations. I don't know if that was too fast or too complicated to follow. I can, yes, I can write on the screen. Probability of S1, S2, Sn given mu. This is what you want to find, to be precise. Mu, the mu of interest, let's say mu star, is the argument that maximizes the probability of this data under some mu temperature. Is this fair? Do people buy this? Cool. So people buy this. Now, furthermore, if this maximizes this and log is a one-to-one function, I'm going to say it also maximizes the log likelihood. And now, because I know my data is IID, like we said before, we can factorize this. S1 S1 given mu, P of S2 given mu, P of dot dot. This is a product, right? P of Sn given mu. This can further be written as argmax ln P of S1 given T and mu times P of T given mu. Am I correct? I think I'm correct. This integral multiple yeah, T1 given mu times P of S2 given T2 comma mu, P of T2 comma mu, and oh, oops, I can't even scroll. Beautiful. Okay, minimize me. Okay. Dot dot. It's my annotation. Oh no. Okay, and so you're integrating this over all your T variables, right? I think so. Yep, dti. Because now you know that this conditional independent statement conditioned on this variable mu is independent of s. So that's why you can remove this mu from here and arrive at this formulation that they show you here. So I don't know, hopefully that helped you become more clear with what this notation is and why it is relevant. So this is maximum likelihood, the same as we did right before this in the lecture. And this is nothing, this has nothing to do with variational inference yet. Let me clear out all of this. And then we can make this the same thing I'm encoding in model form. Oh, whoops, all of my screen is obscured. Undo, clear, cancel, move. Sounds good. And so, okay, so now we have certain observations that are given to us. Someone saw these in the world, and our goal is, given all of these separate observations, we want to find the mu t, like what is this mean temperature that from which this is drawn. And so we write out our model for the world, which is that there is some mean temperature. And then for all these observations, first you draw a certain temperature variable from this temperature distribution. And then you draw the sensor measurement for that temperature variable. And you do this for each of the observations, right? And this is the model that we think defines the world. And what we want to find, which is where we use our guide, you say that for each sensor, like for each observation that we see, there is a certain mean there is a certain scale for this sensor. Oh, okay. So your A and B are now your mean and scale explicitly. And there is a certain temperature variable that is drawn from this normal distribution of mean and scale, right? So you're telling it how you want to condition this model and what you want to approximate this model with. And obviously you care about this mean variable I, mean I, because that tells you the mean temperature, and you do this for all over the observation. So now when you run your variational inference, well, you get an estimated mean temperature of 19.11 whatever. And well, you're not actually I should be clear. Actually, not. Instead of so far we did maximum likelihood learning, right? Because we set the we said that there is we set the mean to this observation sensor value. We set the scale to 1, and we said this is drawn from a certain fixed mean and scale, and find this mean for us after updating it. Got it. Yeah, that's why this is maximum likelihood learning. So a slightly different way we can do this is, and this is interesting because now I'm learning this myself. I probably didn't understand this distinction very clearly before. What's the difference between the maximum likelihood model and the variational inference idea? Here we think the mean temperature. Okay, the mean temperature is drawn from a normal distribution 15 with a scale 2. And for your in range observations, for all your observations, first you draw the temperature from this mean temperature distribution, from a normal distribution parameterized by the mean temperature, and a scale, and the sensor is drawn from this normal distribution parameterized by this temperature and a scale of 1, and now conditioned on the sensor observations. How is this different from the maximum likelihood case? And this is interesting.
The mean temp one is different, right? Because earlier we took mean temp as a parameter, and here we are taking.
Yeah. Okay. So the difference between maximum likelihood and map, basically. Oh, this is a good example to give the kids. Okay. So now we define a prior over the mean temperature instead of setting the mean to a fixed value. I don't know if everyone is clear on this, but this is super important, what Deep just pointed out. The difference between maximum likelihood learning and maximum a posteriori learning is priors. So if you're unclear, please pause and ask me, because I was just unclear 2 minutes ago. Okay, so in maximum likelihood learning, we fix this mean to a certain value and then we update that value. That's how this works, right? The rest is the same. But in maximum a posteriori learning or in Bayesian inference, we don't fix this value to a certain temperature. We now say that it is drawn from a distribution. So we place a prior over it. It's now no longer a tensor 15. Look at this part specifically. This is mean temperature is a sample from this distribution versus, and now we go back. Here, mean temperature is a parameter, not a sample. It is no longer a random, it is still a random variable. It is not drawn from a distribution. It can be changed, but we don't know what distribution it is from. It is just a value that shifts, right? There is no longer a distribution over it and it is drawn from it, right? So here, cool. So this is clear. This was very helpful. Thank you. And let's see what is the difference in the guide that we want now. So in the guide, or what we want to learn, it says there is a certain mean for this temperature mean. It is a certain scale for this temperature scale. So parameters that determine where this mean lies, then this mean that determines where the temperature lies, and then the temperature that determines what the sensor measures. Does everyone buy this? So again, you're adding a level of parameterizations for each random variable that you consider, because in the Bayesian where you place a prior on everything that you're uncertain about. You don't assume starting values, you assume priors.
So you mean to say that here mean scale and mean temp are priors, right?
Are parameters for the prior placed on the mean temperature.
Right. So you take that from a distribution.
Correct. You take the mean temperature from a distribution.
Yeah.
If I ordered, this can go on infinitely. Like I can place a prior on this mean, I can place a prior on this scale, and like keep building up. But like at the end of the day, I need enough data to learn all of these priors, and that comes across very clearly now. That if I have 10 levels of that, that's why they call them hierarchical Bayesian models, because this is a hierarchy. So you started with temperature, in the model, you started with sensor, then one level up you went temperature, then one level up you went mean temperature, then you went mean of mean temperature. You can go mean of that mean of mean temperature and keep going up. So that's interesting. But yeah, that's what we want to do. And so with this guide now, you can learn the mean of the mean temperature with the same stochastic variational inference. And I really want to get to one last cool thing before ending for the day. But I will let this learn first. So let's be clear that this result is not a point estimate, but it is a distribution. So this mean temperature is drawn from this distribution, which has a certain center point and a certain variance, right? Everyone good on this?
Yeah, just to be clear, earlier the prior that you had considered, so in that scale was taken as 1, so that is for a normal distribution, that's why, right? So you
Yeah.
consider it, all right, yeah.
You can take it as 2, you can take it as 3, it will update accordingly. So let's try it out. This is again, like all of these priors are just assumptions that we place on our learning, and it just updates according to the data that we have. That's why, can you tell me under what assumption your maximum likelihood and maximum a posteriori estimate will be the same? If I place informed priors on this maximum a posteriori estimate, so I do give this model a little bit more information. I don't give the maximum likelihood estimate does not take any additional information on the data, right? So under what condition will both of these give you the exact same result? And as a hint, so one is uniform prior, but I'm telling you that I'm not placing uniform priors. I am giving this maximum a posteriori estimate some more information. And then the key to this is think about how the learning update works. So in maximum likelihood, what happens is when you give it data, it updates to some new value, right? Maximum a posteriori, you give it data, it still updates to some new distribution. So at what point will a distribution converge to a value? I guess that's what I'm asking you. Think about it. I'm fairly sure you know the answer. So in one, yeah, annotation, cool. In one, you are going from point to point to point. This is the y-axis and x-axis, let's say, chalo. To point to point, whatever, this is MLE. And in MAP, you're going from distribution to distribution to distribution to distribution to distribution to distribution to distribution. And I've already given you a hint by drawing these things about how these points are affecting the change in distributions. So can you tell me when these two will become equivalent? Under what assumption?
Would it be when sigma is infinitesimally small?
Exactly. So when sigma is infinitesimally small, sigma tends to 0, or your data tends to a fixed point. So if I keep getting this point again and again and again, then my distribution will become peaked, 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 peaked. And then ultimately it'll become a straight line at this point. And then you will say, this is my point estimate. Does everyone sort of understand this? So if you can, yeah.
If it's like a point estimate now, so then basically it is no longer like stochastic, right?
it is still stochastic in the sense that you arrived at this estimate somehow, right? Through a stochastic iterative update procedure.
Yeah.
But there is no
But like,
longer like a uncertainty, if that's what you mean.
yeah. No longer a confidence interval about.
Yeah, in the limit of infinite data. That is one way of saying this. In the limit of infinite data, your estimate will peak. And it will tell you that if this is like a fixed value. Well, I say fixed, but like I just mean the posterior is peaked or sharp. But anyway, hopefully that was clear about like what is the real difference between these two things. And the last thing I wanted to cover is the plate construct, where we know that this is conditionally independent. So we saw this, right? And I told you that given some value of t, the value of mu tells you nothing about the value of s, right? Because you already know the parent, so you can guess the child. Now, knowing about the grandparent is not going to tell you anything more about the child. That's called conditional independence. Now, if there was a separate arrow connecting these two, then conditioning on this would not break the information of this third arrow. So that then they would not be independent. But because that separate arrow is not there, this Sn independent of mu t, sorry, Sn independent of mu t given Tn. That statement holds, or equivalently Si independent of mu t given Ti. And so this next line expresses the same thing in a graphical model form. So for every Si, you only need to know the Ti, and mu t does not matter. Mu t is outside of this. So this box is like a plate, and that plate has, let me draw it a little better. This indicates that there are multiple different plates behind this. Specifically, they write a number n here that indicates how many plates there are, but they haven't written it. Anyway, that's the idea behind plate notation. And the way we write that in model form is that we say, instead of the for I in obs, so for instead of doing this independently for every observation, now we know this conditional independence. So we can parallelize across all of these plates, right? Every one of these can be handled in a separate thread. So that's what this plate notation is saying Pyro should do. And that is super cool because now this is all parallelized. And now it doesn't have to be sequential, so you get a speed up. And this is called a global random variable. This is called a local random variable. But yeah, this is all graphical model stuff. The real thing you need to care about is this highlighted line, because this allows you to parallelize your temperature calculation in your model. And so now with your guide in the same pyro.plate notation, your inference should be much faster. So you should, it seems like, yeah, it completed in 3 seconds, giving you a very similar value as before. So super useful to know about this plate notation. But also, like, you need to know this conditional independence stuff in order to be able to write about this plate notation. And so we've covered a bunch of things. I skipped over the mathematical definitions and stochastic variational inference, but that part is a bit challenging for the audience today, especially since we have new people. I didn't want to confuse all of them. And we have walked through this math in Akash's lectures. So yeah, I'm happy to go through it separately and take questions for about 5 minutes, after which I will have to go.
Yeah, so I was curious, like, even here the MAP estimate is still giving a point estimate, right? But just because we have gone one level above, like that's why we are able to get the probability distribution of the level below it. Like here, because we have we are getting point estimate for the mean and the scale of the distribution of the temperature mean.
Mhm.
At the end, like MAP just gives us a point estimate, right? It doesn't give us,
Of the top level parameters, yes.
yeah. So like the
The global parameters, yeah.
yeah, for like for the thing that you are trying to optimize using MAP, it gives us a point estimate for that.
Yes. Hello. I'm sorry, had to cut a call. I was just saying, yes, at the top level, it will give you a point estimate, but that is the point. Like those are the parameters that parameterize these distributions. So in theory, you can also, not in theory, like even in practice, you can place priors on those and priors on those and priors on those. Like you can keep going infinitely, placing priors on stuff, but at some point you have to stop. Like at some point you have to consider that, okay, now this is the level of uncertainty I'm willing to work with. And yes, that's where you stop.
Yeah, then in similar way, like even MLE would be able to give us the distribution, correct? If we had gone one level above them.
Yeah, like map is MLE plus priors, right? If that's what you're asking.
Yeah.
Yeah. Cool. Any other questions? Okay, if not, then I will share this notebook and I will take your leave. Okay, I will see you guys next week and good luck for tomorrow. I will post an update about my office hours. If anyone else is volunteering for office hours this week, please let me know. I'll set up a meeting for you. I'm doing one on Tuesday evening.
How many are we
Thank you
thinking
for that.
of?